Hello everyone, this is video 12.3. We're going to be looking at the areas of triangles. So the previous sections we've looked at the areas of rectangles, and then we've looked at the areas of essentially parallelograms and what we could call compound quadrilaterals, where we've taken two quadrilaterals, typically rectangles, and either put them together additively or subtracted them apart. So now we're going to be moving into the areas of triangles before we start looking at the areas of other sort of more complicated polygons. So again, like any of these videos, you may want to go back and look at the previous 12.1, 12.2 videos, and then again 12.1, you may want to go back and look at chapter 4. So just make sure that you've done all the sort of like requisite work before starting this section. All right, let's get going. So there's two ways I want to look at the area of a triangle with you, and this is going to be the first one. And so I found this image on Google image search, and we've got this triangle here, the yellow triangle. Now, specifically, we can see that it's a right triangle. So this is a very specific case. This is a very specific case to right triangles, and we can see we've got the base here, we've got the height here, and these are the base and the height of our triangles. Now, remember, these need to be at a right angle to each other. There's a slide here in a moment, so we'll kind of reinforce that idea. But you could see how we could take the copy of this triangle and reflect it up here. Or really rotate it up there. If it reflected it, it would make a kite instead of a rectangle. So we're going to take this copy of this yellow triangle, and then it rotates up there, and it makes this rectangle. And so we've got the area of the rectangle is base times height. It's this length times this length. And so since we know that the white triangle area is the same as the yellow triangle area, then we know that the yellow triangle is half of the rectangle in terms of area. So if the area of the rectangle is base times height, then the area of the triangle would be 1/2 of that, 1/2 the base times height. Now, I know it's a little strange because typically when we talk about the area of a rectangle, we would say length times width. We don't really say base times height very often for the area of a rectangle. And I think, whoever made this image did that to sort of reinforce this sort of traditional way we think about this formula. It's not incorrect, it's just a different way of stating it. Um, but I think that's kind of what they had in mind by using base times height there. Um, so this is one way of thinking about it. And again, we can see we've got the right angle here, and it's a special case because it allows us to get directly to this rectangle really in one step. So let's look at the more general case here, a triangle that is not necessarily a right triangle. And don't get confused. I mean, there are right angles all in this diagram. There's one here, and there's one in here. But none of the angles of the triangle itself are right angles. This angle B looks like it might be a right angle, but we're going to assume that it's not, and without really any loss of anything. So we're going to put in this height, and it comes down here, and it is going to be at a right angle to our base. So really what we've done is we've taken this triangle, we've broken it up into two triangles. And then each of these two triangles actually fit the case of the previous slide. This sort of orange creamsicle looking colored triangle is going to rotate up here, and then this orange creamsicle part is going to rotate up here. And so we know that this part, this white triangle here, is going to be equal in area to this part here, this orange creamsicle part here, and then on the right side, this area is going to be equal to also this area. So really, it's the exact same case that we had in the previous slide. We've just taken our triangle, broken it into two triangles that work with that case, and so we can see that the area of let's go back here. So the area of the rectangle, so the area, and then we'll draw a little rectangle down here in the subscript to show we're talking about the area of the rectangle, is this base, this whole base, times this height, which is the same as this height, which is the same as this height. And again, this is all a property of it being a rectangle. So we know that all of these heights, this whole thing is the base. This base is from here to here. It's this whole thing. So the area of the rectangle is the base times the height. Now, if we wanted to, we could go through and break the area of this rectangle now into these two smaller rectangles. We call this base 1 and base 2. We could break this up into smaller parts and work through the algebra more if we need to. It's probably not going to be necessary for the level at which we're trying to be convincing about this. But we see now this triangle is half of this rectangle because both parts of that triangle have been duplicated. So now we've got that the area of the triangle is 1/2 the area of the rectangle. And so the area of the triangle, the area of the triangle is going to be 1/2 the base times the height, or as we usually know it, just 1/2 base times height without the parentheses. So again, just to reinforce, typically when we're talking about rectangles, we are talking about length and width, or length and height, or width and height. We're using sort of those dimensional terminology. When we start talking about a triangle, we convert that into talking about base and height. It's not really a huge difference. It's just the context. I don't know that I've ever necessarily seen the area formula for a triangle is 1/2 length times height or width times height, although you certainly could. I mean, we just need to know that they need to be at right angles to each other. So it's a little bit of a confusing point, for some students, maybe even for you as well, like why we have the same terminology or different terminology for the same thing. But it's representing the same idea. So just make sure that you understand that, for different contexts, which terms we typically use. The base of the triangle could be any one of those three sides, and then the height is going to be perpendicular to that base, although it does not necessarily need to actually intersect visibly at that point. We saw that in the previous video where the height was outside of the triangle, and so it didn't actually intersect with the line segment of the base, but it is perpendicular to the line containing the line segment of the base. So that base is a segment. If you were to continue extend it out into a line, it would intersect and form a right angle. So just make sure you understand the different contexts for rectangles and triangles is really the point. This is the same thing I just did at the top of the third slide, just kind of working through the area of the triangle. We know is going to be half of the area of the associated rectangle. So the area of the rectangle is the length times width, or length times height, or whichever dimensional terminology we want to use for rectangle. And again, that gets us to the 1/2 base times height. So I found this image, and I thought it was a really interesting set of problems involving the areas of triangles. And so if you look at the first triangle, you can see that the 4 and the 9 centimeter lengths are the bases and the heights. Now, there's no right angles that are explicitly shown here. But again, I'm not going to do anything like this that's meant to be like intentionally tricky. So for something like this, we're going to, it's not explicitly stated, but we're going to say that these are all at right angles to each other. So we'll make this a little bit more clear. So the area of this triangle would be 1/2 4 times 9. So this is my base, this is my height, I got the 1/2. And again, you could see, if we extend this out, how this would be 1/2. This reflects there, this makes that. So this would be half of a rectangle that is 4 by 9. So this would be 9, this would be 4. So it would be 1/2 of the 4 by 9, 1/2 of the 36, so the area would be 18. Now, if we look at shape 2, how is this area different? For a lot of students, they're going to see this and it's going to look like a very, very different problem, although hopefully most of you recognize that it's exactly the same thing. The only difference is that here my base is horizontal and here my base is vertical. So again, this variability principle that we want students to see these shapes in many different forms. so they don't think that the base has to be the horizontal side of the shape. So there are a lot of students who will look at this triangle and panic that there's not a base because there's not a perfectly flat horizontal side to this. Now, keep in mind this 4 centimeters is horizontal, but by the definition that the book states, the base needs to be a side of the triangle. And so this 4 couldn't serve as the base because it's horizontal, but it's not a base of the triangle. So the 9 would have to be the base, and then this would be the height because it's the perpendicular to that. So when you go back and look at that definition of the base needs to be a side of the triangle, but there's nothing that says that it has to be a horizontal side, although that's the way a lot of math teachers draw it 90, 95, sometimes even 100% of the time. So we want to get away from that and show triangles where the base is not always horizontal. Now that I've said that, the base is horizontal for the next 4 problems. But for problem 3, you see this is my base here, and now this is my height. And so you can see the difficulty the students may have with this problem. That now we've got our base, we've got our height, but the height and the base don't actually intersect. Here they do, here they do, here they don't. But again, we saw in the previous slide, this is not necessarily a problem. We just need to look at the line that contains the line segment of the base, and we see that it would hit and that it would form a right angle. So this works as well. Triangles 1, 2, and 3 all have the same area. I mean, they all have the same area. They're very different representations of this triangle. They're very different looking triangles. We can see triangle 3 is an obtuse triangle. 1 and 3, I'm sorry, 1 and 2 both look acute, but 3 is obtuse. But they all have the same area, and they're all 1/2 4 times 9. If we look at the next 3 triangles, draw the line here. And so we can see problem 4 is a lot like problem 3. Again, we have this sort of external height. So we have this question about how does this intersect the base? Well, it doesn't hit the actual base, but it hits the line containing the base. Problem 5 is a strange one because the height we could have drawn inside where it would hit, but it's drawn outside. And is that a problem necessarily? So again, if we think about this rectangle containing all of this, we could draw the height here, we could draw the height here, we could draw the height here. It doesn't change the length of that height. So drawing this height externally when it could have been drawn internally, not really a problem. Now, the book definition does say that the height should go from the vertex point. It should go from the point of the triangle that's not part of the base. So you can see that the base contains these 2 points here. And so the height should go from that 3rd point down to that base. So by the strict book definition, this kind of wouldn't work as the height because it's not starting at that vertex. But we can see geometrically that it does work because it's the same length. So I guess if you really wanted to split hairs, we could say that this is not the height as it should be shown in the triangle, but it has the same length as the height. That's pretty semantic. And now this triangle 6, let's go back to this one. This triangle 6 is pretty complicated as well because now we've got the height external to the triangle, so we've got the same difficulty as triangle 5, but now we've switched the 5 and the 9. And so does that change the area at all? Do 4, 5, and 6 still have the same area as 1, 2, and 3? So I'll leave that for you to think about if that's still the case or not. Hopefully it's not posing too much problem for you there. But like I'll say at the end, if you have questions about what happens with 4, 5, and 6, bring those to class. I included this picture for one reason only, and that's because this 66 millimeters. So if we were to give this problem to a class and say, okay, find the area of this triangle, hopefully students would recognize that this 21 is the height, this 33 is the base, and so the area would be 1/2 the base. Forgot my units there. 33 millimeters times the height of 21 millimeters. So the question is, why is it 66 here? Realistically, that 66 is only there as a distractor. It's there to see if students sort of understand um, the base and the height. A lot of students are going to want to use this 66 for something. And so I would really expect a lot of students to do the area is 33 times 21 times 66. Just start multiplying things together. Or that they would do the area is 1/2 33 times 66. That they think that the base and the height have to be sides of the triangle, and the 21 is not the length of a side of the triangle. So the 66 might make more sense for some students as the height than the 21. Uh, it's a little bit of a distractor. It's not there to be tricky necessarily, but it's there to allow us to see how well students understand this idea of base and height of a triangle. Problems that we ask about the area of the triangle sometimes deal more with assessing how well students understand the concept of base and height than the concept of area of a triangle. So if we were to see students doing 33 times 66 or 1/2 33 times 66, that's a pretty clear indicator to us that we need to go back and review the properties of base and height. So it's okay to include sort of extraneous information like this purposefully. So we see how students work with this little extra bit of information. The last thing I wanted to look at is this thing called a geoboard, and in a physical classroom, bring in a set of these geoboards. You may have seen these before. Um, Sometimes they're wood, sometimes they're plastic. Sometimes in a school, the industrial arts class will go through a project of making some geoboards. There's a piece of wood, little nails hammered in, and they're arranged along this like square lattice, which just means that they're placed regularly to form like little squares like this. And so they're going to make this they're going to make these squares essentially. And so the idea is that you take rubber bands and then you wrap them around these pegs and they make little shapes. And so we could take a rubber band and wrap it around these two pegs and then pull it tight to this peg and then it comes down this way. And so then we could use this geoboard to make triangles and then find the area of that triangle. And so what would be the area of this triangle? And so what students a lot of times will do is they'll take a rubber band and they'll put it around this rectangle. And then they'll take a rubber band and put it around this square. And so they'll say, okay, well, this square has an area of 16. Now, you gotta be really careful in working with geoboards. This is really the main reason why I wanted to use this example. A lot of times students will count 1, 2, 3, 4, 5, and they'll count the pegs and they'll say this square has an area of 25. And that's wrong. If you go back to the very beginning of the chapter that we talked about tiling these with little squares. And so if I tile this with these little squares along this square lattice, you can see that the area is actually 16. So this can be really tricky for some students because they want to count the pegs or the nails, and they should be counting the spaces between the pegs. So the area here is not 25, but rather 16. And so then the area of this part of the triangle, so the area of triangle 1 is going to be half of 16, which is 8. And the same thing here. This is 1, 2, 3, 4. And so this rectangle has an area of 4, so the area of this triangle, the area of triangle 2 is going to be 2, so 8 plus 2. This whole triangle then, so the area of the triangle is 8 plus 2, which equals 10. But if students are counting pegs or nails or however you want to think about it, instead of the spaces in between, they're going to get the wrong answer. So really be careful. Watch students if you're working with geoboards that they're counting the right thing. And I mean, heck, you be careful working with a geoboard problem. Make sure you're counting the right thing. All right. So for your checkpoint problem, I want you to look at this triangle here. I want you to find the perimeter and the area. We haven't talked about perimeter in a while. And so hopefully one of the things you'll notice is very similar to the triangle that we looked at before with the 66 millimeters. For the perimeter, you're going to use some values but not others. And for the area, you're going to use some values and not others. And you're going to have some values that get used for both, and you're going to get some that get used for one or the other. Are there any values that we could put in this triangle that would get used for neither? So as it turns out, every value that we have gets used for something. But is there a way we could put in a value that gets used for neither? So I'll leave that problem with you. If you have any questions about this problem or anything else from the video or from the book, please, as always, let me know. All right, thanks.